Imagine an aircraft flying thousands of feet above a desert battlefield, a burning forest, or a crowded coastline. Yet inside the cockpit there is no pilot, no breathing human being, no heartbeat reacting to turbulence. Only sensors, cameras, antennas, and a silent stream of data traveling at the speed of light across satellites until it reaches a control station where a human operator sits in an air-conditioned room holding a control stick like a video game controller. This is the world of remotely piloted aircraft, often called RPA, the technological bridge between aviation and robotics that has completely changed how humanity observes, protects, fights, explores, and understands the sky. A remotely piloted aircraft is not simply a drone toy you see in parks. It is a certified aviation system consisting of 3 core elements: the aircraft itself, the ground control station, and the communication link that binds them together into one intelligent flying machine. And the most fascinating fact is that legally and technically the aircraft still has a pilot, just not inside it. The story begins long before modern wars and modern cameras. The concept of pilotless flight appeared during World War I, when engineers imagined aircraft that could carry explosives without risking pilots, but technology was not mature enough, and radio communication was unreliable. However, the dream never died, and during World War II, target drones were developed to train anti-aircraft gunners, creating the first operational unmanned aviation environment. The real revolution began in the late 20th century when satellite communication, digital sensors, and GPS navigation allowed aircraft to be controlled across continents, turning the remotely piloted aircraft into a persistent eye in the sky, capable of staying airborne for more than 24 hours continuously, something impossible for human pilots due to fatigue and biological limits. To understand an RPA deeply, you must imagine it not as a plane, but as a flying sensor platform, its wings designed for endurance rather than speed, its fuselage filled not with seats, but with avionics racks, electro-optical cameras, infrared sensors, synthetic aperture, radar, and sometimes communication relay systems. These payloads allow operators to see at night through smoke, through clouds, and even detect heat, signatures of engines, or humans from kilometers away. The ground control station is equally important because it is effectively the cockpit. Inside it, pilots monitor altitude, speed, attitude, fuel, and engine parameters exactly like a traditional aircraft, while sensor operators control cameras and tracking systems. And mission commanders analyze live intelligence in real time, making RPA operations more like a flying command center than a single aircraft flight. Communication links are the lifeline. Line-of-sight radio is used for nearby operations, but satellite links enable intercontinental control, meaning the aircraft may fly over one country while the crew sits in another continent, a concept that redefined aviation regulations and international law, because now the physical pilot location and aircraft location are separated. One of the most well-known advantages of remotely piloted aircraft isn't a large RPA such as a high-altitude long-endurance platform can remain airborne for over 30 hours, monitoring borders, tracking storms, mapping terrain, or supporting rescue operations without risking human fatigue. And because there is no onboard pilot, the aircraft can be lighter, more fuel-efficient, and capable of dangerous missions like flying into volcanic ash, nuclear contamination zones, or hurricanes where sending a human pilot would be life-threatening. Militaries adopted RPAs rapidly because surveillance is the foundation of modern strategy. Instead of sending manned reconnaissance jets for short missions, commanders could now maintain constant observation over an area, detecting movements, preventing ambushes, and coordinating operations in real time. But focusing only on warfare hides the much broader impact, because today RPAs inspect pipelines, monitor crops, deliver medical supplies to remote villages, map disaster zones after earthquakes, and even assist scientists in studying wildlife migration without disturbing animals. The aviation classification is also important. Small RPAs operate below controlled airspace and are often electric-powered. Medium tactical systems support regional surveillance, and large certified remotely piloted aircraft operate in controlled airspace alongside commercial airliners using transponders, collision avoidance systems, and strict aviation procedures. proving that they are not separate from aviation but an evolution of it. Safety systems are critical because losing communication could be catastrophic, so engineers developed fail-safe modes such as return to base, navigation using GPS, autonomous landing protocols, redundant flight computers, and multiple communication channels. Modern RPAs can continue flight safely, even if contact is temporarily lost, demonstrating a level of autonomy that gradually approaches self-flying aircraft, though human oversight remains essential. The psychology of RPA piloting is also unique. Pilots must rely entirely on instruments and video feeds, feeling no acceleration or wind, which requires specialized training, because spatial awareness comes from sensors instead of human senses. Yet the responsibility remains identical to manned aviation because they control real aircraft in real airspace, affecting real lives. Regulatory authorities around the world faced major challenges integrating RPAs into civilian skies. Air traffic controllers needed identification systems, separation standards, and communication protocols, leading to technologies like a DSB integration and detect and avoid radar that allow unmanned aircraft to sense nearby traffic and maneuver safely, moving aviation toward a future where autonomous and human-piloted aircraft share the sky seamlessly. The economics are transformative as well. Operating an RPA costs far less than maintaining large manned reconnaissance aircraft. Fuel consumption is lower. Crew requirements are smaller and maintenance cycles can be optimized due to simpler cockpit systems, enabling even developing countries and research institutions to access aerial intelligence previously available only to major powers. Environmental monitoring has become one of the most positive uses because RPAs can track oil spills, glacier melting, deforestation, and ocean pollution, continuously providing scientists with long-term datasets impossible with short-manned flights. In agriculture, they analyze crop health using multispectral imaging to detect water stress and disease before visible damage occurs, improving food production efficiency worldwide. Communication relay RPAs act as temporary flying cell towers during disasters when ground infrastructure collapses, restoring connectivity for rescue teams and civilians, proving that the same technology once designed for military observation can save lives in humanitarian crises. Yet ethical debates also emerged, especially concerning privacy and surveillance, because a persistent aerial camera raises questions about civil liberties, forcing governments to develop laws governing where and how remotely piloted aircraft may observe civilian populations, balancing security and personal freedom in the digital age. Technologically, the heart of an RPA is its flight control computer, using gyroscopes, accelerometers, and GPS fusion to maintain stable flight automatically. The pilot commands direction and mission decisions, while stabilization is handled by algorithms hundreds of times per second, making flights smoother than human reflexes could achieve, and demonstrating how aviation increasingly relies on software as much as aerodynamics. Power plants vary from electric motors for small systems to turbocharged piston engines and turboprops for large endurance platforms, optimized not for speed, but for fuel efficiency at high altitude, where thin air reduces drag. Wings are long and slender, similar to gliders, maximizing lift-to-drag ratio, so the aircraft can circle an area for hours using minimal energy. Sensors have advanced dramatically. High-definition electro-optical cameras provide day imagery. Infrared detects heat at night. Radar maps terrain through clouds, and signals intelligence packages intercept electronic emissions, turning RPAs into multi-domain information collectors. In search and rescue operations, they locate lost hikers through body heat signatures, guide helicopters to survivors, and drop emergency supplies before rescue teams arrive, shrinking response time from hours to minutes. From a systems perspective, an RPA mission is data-driven. Information flows from sensors to operators to decision-makers, instantly making it not just an aircraft, but part of a larger information network, known as network-centric operations, where the value lies in knowledge rather than physical presence. Looking at the future, engineers are working toward increased autonomy, where aircraft can taxi, take off, navigate and land with minimal pilot input while still under human supervision, similar to autopilot evolution in commercial aviation, but extended to full mission capability. However, complete removal of the human pilot remains controversial due to accountability, safety, and ethical control considerations. Ultimately, the remotely piloted aircraft represents a shift in aviation philosophy from transporting humans through the sky to projecting human awareness into the sky, extending our senses beyond physical limits. And as you realize this transformation, you understand that RPA is not just another aircraft category, but a new chapter in the relationship between humans and machines, where distance no longer separates pilot and aircraft, and the horizon is no longer the boundary of observation. And this is only the beginning of the story, because the technology continues evolving towards smarter, safer, and more integrated airspace operations, setting the stage for a future where the sky itself becomes a connected information environment rather than empty air. And when we look up and see nothing, we may still be watched over by a silent guardian whose pilot sits far away yet remains fully present in the mission. As remotely piloted aircraft technology matured, engineers realized the greatest transformation would not come from making one aircraft smarter, but from connecting many aircraft together into coordinated systems. And this gave birth to swarm capability, where multiple RPAs share information with each other in real time, distributing tasks automatically so that one monitors, another relays communication, and another tracks movement, functioning less like machines and more like a living network in the sky. A concept inspired by birds flying in formation yet powered by artificial intelligence algorithms, calculating spacing, trajectory, and collision avoidance thousands of times per second. In disaster zones, this means dozens of aircraft can map a collapsed city within minutes, generating a full 3D model for rescue planners before ground teams even arrive. While in maritime operations, swarms can patrol vast coastlines, detecting illegal fishing or smuggling vessels continuously without interruption. This evolution introduced the idea that future airspace will no longer be dominated by individual flights, but by intelligent traffic ecosystems, where each aircraft constantly broadcasts position, predicts future movement, and negotiates safe paths automatically. And to support this environment, aviation authorities began designing unmanned traffic management systems, digital airspace layers where autonomous and remotely piloted aircraft coordinate, similar to internet data packets routing through networks, dramatically reducing controller workload while maintaining safety. Another major development is artificial intelligence-assisted piloting, where onboard computers can recognize objects such as vehicles, humans, fires, or damaged infrastructure without constant operator control, allowing crews to supervise multiple aircraft simultaneously rather than manually steering each camera, transforming pilots into mission supervisors and analysts rather than traditional stick-and-dooter aviators. This does not remove the human from decision-making, but amplifies human awareness, giving one crew the observational power that once required dozens of aircraft and personnel. Civilian industries quickly embraced these capabilities, and infrastructure inspection became one of the most economically valuable applications, because power lines, bridges, wind turbines, and oil refineries require constant monitoring, yet are dangerous and expensive for humans to inspect directly. RPAs equipped with high-resolution imaging and laser scanning now detect microscopic cracks or overheating components long before catastrophic failure, preventing blackouts and industrial accidents while saving billions in maintenance costs. In agriculture, precision farming expanded further as RPAs not only detect crop health but also spray fertilizer and pesticide precisely where needed, reducing chemical usage and environmental damage, and farmers in remote regions use them to survey fields, monitor livestock, and predict irrigation requirements using thermal data, showing that aviation technology, once linked to warfare, now contributes directly to global food security. Urban environments introduced a new frontier where small cargo RPAs deliver medicine, blood samples, and emergency equipment across traffic-congested cities in minutes rather than hours. And although large, passenger transport by remotely piloted aircraft remains under study, the safety logic is compelling because computers do not become distracted or fatigued, and redundant control systems can exceed human reaction speed, yet public trust and certification standards require extremely rigorous validation before such operations become routine. Safety remains the core principle guiding development, and engineers implemented detect and avoid systems combining radar optical sensors and predictive algorithms, capable of identifying birds, buildings, and aircraft simultaneously, enabling RPAs to maneuver autonomously if a collision risk appears even before the remote pilot reacts effectively, adding a digital co-pilot that never blinks, Combined with encrypted communication links and multiple backup satellites, modern systems maintain control reliability exceeding many early manned aviation technologies. However, the reliance on data links introduced cybersecurity as a new aviation discipline, because protecting command signals from interference or hacking became as critical as protecting engines from failure, leading to layered encryption, authentication protocols, and autonomous contingency behavior where aircraft automatically return home or land safely if abnormal commands are detected, demonstrating how aviation safety now includes digital resilience alongside mechanical reliability. Alongside growth came the development of counter-RPA technology, because unauthorized drones near airports or sensitive facilities pose serious hazards. So radar-tuned to small targets. Radio frequency detection and interceptor systems were created to identify and neutralize rogue aircraft, proving that the sky of the future will be actively managed not only for safety, but also for security. Ethical discussions expanded beyond privacy into accountability, asking who is responsible if an autonomous decision leads to damage: the manufacturer, the operator, the programmer, or the authority approving integration. And aviation law continues evolving to define responsibility frameworks, ensuring technological progress does not outrun moral governance. From an educational perspective, new career paths emerged, including remote pilots, sensor operators, data analysts, autonomy engineers, and unmanned traffic managers, reshaping aviation workforce training where understanding software, networking, and robotics becomes as important as aerodynamics and meteorology, illustrating that aviation is transitioning from mechanical engineering dominance to interdisciplinary digital systems engineering. Technologically, the aircraft themselves are becoming more efficient through composite materials and solar augmentation, allowing some high-altitude RPAs to remain airborne for days by harvesting sunlight during daylight and conserving energy at night, effectively creating pseudo-satellites capable of providing internet coverage or environmental monitoring at a fraction of satellite cost, and with the advantage of recoverability and upgrade. Scientific exploration benefits enormously because RPAs can fly into hurricanes to measure wind intensity, into polar regions to track ice thickness, and into volcanic plumes to sample gases without risking human life, producing climate data that improves forecasting models and disaster preparedness worldwide. The integration with commercial aviation continues gradually. Test corridors now allow large RPAs to share controlled airspace using standard radio procedures and transponders, meaning the airliner cruising above you may soon share the sky with an unseen aircraft, performing survey work safely separated through coordinated automation, and passengers may never notice because the system is designed to be invisible yet reliable. Philosophically, this technology changes humanity's relationship with distance, because historically, exploration required physical presence, but remotely piloted aircraft project awareness without relocation, allowing societies to monitor oceans, forests, and borders continuously and respond faster to emergencies, shrinking the functional size of the planet by reducing reaction time rather than travel time. The next step is collaborative autonomy, where RPAs interact with ground robots and manned aircraft, simultaneously forming integrated rescue networks in which aerial units locate survivors, ground robots reach hazardous areas, and helicopters extract victims guided by shared real-time mapping, turning disaster response into a coordinated choreography rather than chaotic improvisation. Economically, nations investing early in RPA infrastructure gain advantages in logistics, environmental protection, and digital mapping accuracy, which supports urban planning and transportation optimization, indicating that unmanned aviation is becoming foundational infrastructure similar to telecommunications or GPS, rather than a niche technology. Yet despite automation growth, the human element remains central, because judgment, ethics, and strategic decision-making cannot be reduced entirely to algorithms. Remote pilots still interpret context, confirm targets, prioritize, rescue, and ensure proportional response, meaning the future is not humans replaced by machines, but humans extended by machines. A partnership where technology carries risk while people carry responsibility. As research pushes toward optionally piloted aircraft capable of switching between onboard and remote, control aviation may experience a hybrid era, blending traditional cockpits with remote oversight, providing redundancy in emergencies, potentially preventing accidents caused by pilot incapacitation, while preserving human authority over flight decisions. Ultimately, the remotely piloted aircraft represents the convergence of aviation, computing, communication and ethics into a single system that transforms the sky into an information layer surrounding Earth, constantly sensing, analyzing, and assisting life below. And when future generations look back, they may not define aviation solely by carrying passengers across continents, but by how humanity learned to extend perception beyond the cockpit and maintain awareness of the entire planet in real time. The powerful truth is that RPAs did not remove humans from the sky. They placed humanity everywhere in the sky at once, allowing a single individual to protect wildlife in Africa, guide rescue in mountains, monitor storms over oceans, and deliver aid to isolated communities within the same day, proving that the greatest achievement of this technology is not mechanical efficiency, but expanded human capability. And as the silent aircraft continues circling high above unseen, yet vigilant, it symbolizes a new era where distance, danger, and darkness no longer prevent observation or assistance, reminding us that aviation's ultimate purpose has always been more than transportation. It is connection, awareness, and guardianship of our world. And the remotely piloted aircraft stands as one of the clearest signs that the future of flight is not just about reaching farther horizons, but about understanding and protecting everything beneath them.